Greetings all. This is lesson number 1 from chapter 2. Most of the contents of this chapter you probably already know from honors chemistry last year. So again, I'm going to be doing sort of a color commentary, hitting some highlights, mentioning some philosophical ideas and some theological ideas as we go through this chapter, but also I hope to jog your memory from things that you learned last year. First of all, you can see by our title, there we go, Atoms, Molecules, and Ions. And when we think about first-year chemistry at any level, you need to be thinking about little teeny tiny particles moving around and perhaps colliding with each other. And these particles that we normally focus on are either atoms or molecules or ions. These particles may collide, they may come near each other, they may interact, they may repel. There's all kinds of things going on here. They have kinetic energy. This is all based upon the model of an atom that was first articulated 200 years ago by John Dalton. In any case, here's an early periodic table. So we'll introduce the idea of a periodic table in this chapter, but we'll save more details about the periodic table to chapter 7. What you should notice in this diagram, first of all, is that there are a number of spaces where there aren't any elements, which means this is predictive. You would predict that there might be an element that goes in one of these spaces. Perhaps a space would be something like, right here where these dashes are and so forth. And that's one of the powers of a good model, a good organizational scheme, and that is it can be predictive. Another thing you'll notice, it's already anticipating that these particles, at least chemically, do not break up into pieces, but they combine in whole numbers, whole number ratios. You can see this in this column. Another thing you should notice is we have rows, at least in this particular periodic table, just like in the periodic table in your book or on the wall in my room. And so here's column 1, 2, 3, 4, 5, 6, 7. But there are no inert gases that would go over here in column number 8. There are no inert gases or noble gases such as helium and neon and argon and krypton and xenon and radon. Because they don't combine with anything, it's very difficult to detect them because they're not making chemical reactions. We'll comment more on that as the year progresses as well. Some of your larger compounds here actually would go in what we now think of as subshells or sublevels or sub-energy levels. So just a couple of things about this early periodic table. Another interesting thing is that this guy named Newland, his idea of a periodic table was groups of 8, which he called octaves, just like the musical scale. Do, re, mi, fa, sol, la, ti, do. You have 1, 2, 3, 4, 5, 6, 7, the noble gases, 8. He saw them in groups of 8. The main person, though, of course, is Dmitry Mendeleev, Russian, 1870. You can see a picture of him online, of course, or on the periodic table in the side of my room. And he looks rather suspiciously like me when I used to have long hair. It's really uncanny and it's a little disconcerting for me, at least. Finally, you should notice that this periodic table goes by increasing atomic weight. Nowadays, we do it by increasing atomic number, not by increasing atomic weight. And that's a very common test question. All right. Couple of things on this opening paragraph. The chemical elements are forged in stars. Now this raises a very interesting theological question, and it goes back to Genesis 1. God the Creator when God creates, God can create directly, or God can create secondarily using secondary means. For example, you could build a car from its pieces, or you could build an assembly line or a robot to construct the car for you. In either case, you built the car, but in the case of the robot or the assembly line, you used a secondary process to construct that car. And the idea here is that we see heavy elements made out of many, many protons and neutrons and electrons being made or forged in stars. And so it's logical to think that all of these elements that are on our Earth had their origin in star formation, and that maybe God, during his creation week, used stars to create these heavier elements, which later on then, through gravity and perhaps other forces, ended up in accumulated masses that we can call planets. And then he gets busy with his next creation day and so forth. Something to think about. Another idea is the common use of the term building blocks. In organic chemistry, we often talk about amino acids being the building blocks of proteins, or sugars being the building blocks of carbohydrates, or nucleotides being the building blocks of DNA and RNA. The very idea of a building block implies a builder. And so it's very, very difficult not to use teleological language, that is, language that describes a person with purpose, when we look at the complexities and the majesty and the mysteries of creation. Finally, we have this word nature here. You have a human nature. We all have a human nature, and there are differences ultimately in that human nature, but lots of similarities. So this nature is this amazing essence that causes something to be what it is, and it's responsible for properties and structures, as we will elucidate later in the upcoming chapters. But this fundamental essence or nature is again a teleological language, a language with a purpose, and an ontological language, a language that means there had to be a beginner, one who begins, and who's responsible for giving these fundamental particles the unique characteristics which they have. Very interesting. All right, we go now back to 120 some years ago, and we have the developing theory of the atomic model. John Dalton talks about little teeny tiny fundamental particles, which he calls atoms. That original model from 200 years ago has been altered and tweaked, but it was a good starting place. And now we begin to focus in on the structure of those atoms, something that John Dalton would not know anything about. And so we see during the second half of the 19th century, J.J. Thomson, and then into the 20th century, Ernest Rutherford, both playing important roles in helping us to understand that this atom actually has a very, very dense core, which we now call a nucleus. And inside that nucleus, you find the protons and the neutrons, something that were not known about until the 20th century. And somewhere in the space around that nucleus, you have electrons. Now, you notice that there is no border. There is no hard outer shell, so to speak, where inside you have the atom and outside you do not. It's sort of like the atom has this decreasing density of electrons as you go away from the nucleus. It does not have this border. And so in quantum mechanics later, we're going to talk about how we have this imaginary border for an atom, which is the region of space within which 90% of the time you're going to find a particular electron. And so you should know about protons being positive and electrons being negative and neutrons being neutral. Now, the different combinations of these particles help us to understand the properties that the different elements have. By the way, this picture over here is also not really to scale. You can see that if the nucleus were really the size depicted here, the electron cloud would extend over 200 meters. That would be 2 football fields away. Another way of thinking about it is if you had a marble and you put it at second base at Busch Stadium to represent the nucleus, the nearest electron would be in the bleacher seats, which these days I don't even know if I could afford a bleacher seat. All right. The atomic number is simply the number of protons. And oddly enough, we don't use the letter A, we don't use the letter N. To stand for atomic number, we use the letter Z. If you don't like it, tough, deal with it. And it's a whole number. It's an integer. Also, when we talk about atoms, we talk about a relative atomic mass. We're not talking about uncles and aunts and grandpas and grandmas. What we're talking about here, of course, is compared to some arbitrary standard, some atoms are going to have a greater mass or a lesser mass than that standard. And early on, the standard was hydrogen by John Dalton. Later on, that standard became 1/12 the mass of a carbon atom. It's very stable. It's easy to isolate this. And so one atomic mass unit is 1/12 the mass of an atom of carbon, where that's the most common isotope of carbon, a word we'll use a little bit later, made up of 6 protons and 6 neutrons, so it is element number 6 on the periodic table. These are relative masses. I should mention John Dalton was a Christian. He began his profession as a school teacher about the age of 13, and he took many observations of weather, some 200,000 or so, as far as I could estimate. And from the studying of air masses and weather patterns, that's where he came up with his mental model of these fundamental particles called atoms, which are always moving around and colliding. The word atom itself, of course, comes from the Greek word atomos, which was used several centuries before the time of Christ as being some fundamental indivisible particle. We also should mention something about medieval alchemy. This is your forerunner to chemistry. One of the big driving impetuses for alchemy was to figure out a way to turn elements into more expensive elements, like turn lead into gold and so forth. And of course, they had no understanding of the nucleus and no understanding that the only way you're going to pull that off is by adding or taking away protons from the nucleus. Nevertheless, this was the beginning of this field called chemistry. Early on, and this is also important to point out, that the early studies were very quantitative, whereas before they just looked at qualities, visual cues and ideas, color changes, changes in state like gases and liquids and solids and things like that, whether or not they exploded or dissolved. Quantitative was where we begin to actually take measurements. An idea for testing hypotheses born out of the revolutionary ideas that were based upon the Reformation, which was itself based upon the idea of a sovereign God who worked in ways according to his reason and not based upon competing craziness of multiple gods or mysterious things that could never be explained that were magical. By the way, the unit of the atomic mass is sometimes written with the letter U. Sometimes it's AMU for an atomic mass unit. And more frequently, not a lot, but I'm seeing it a little bit more, they're actually calling this the Dalton, named after John Dalton. And 1 Dalton is pretty small, 10 to the minus 24th grams. Now, the mass number is going to be a number that actually reflects the mass of the atom. And almost all of the mass of the atom is located in the nucleus, and the nucleus is made up of protons and neutrons. So the mass number is basically going to be the sum of the protons and neutrons. And we don't use the letter M for mass number or the number sign or N. We use the letter A for the mass number. And again, if you don't like it, tough, deal with it. It's the letter A. Maybe you can think of the atomic mass number, the mass number of the atom, being a reason why it's designated by the letter A. Now, unlike the periodic table at the very beginning of the chapter that I was commenting on, you'll notice that these days we put the numbers on the left side of the symbol and not on the right side. So the number in the upper left is the mass number, which is going to be the protons plus the neutrons. The number down here is going to be the number of protons. Sometimes it's called the charge number. And then, of course, you can have a number in the upper right. And that number is usually the number of its charge if it's an ion. And then the number in the bottom right is the number that we use when we have multiple atoms, such as in a molecule. Now here's a chart showing you the difference between electron, proton, and a neutron. You'll see another chart that I made up years ago that mentions some other things as well. You should know this chart. You don't necessarily have to know these numbers, but if we had the electron as an arbitrary mass of 1, then the proton would have a mass of 1836 and the neutron a mass of 1837, which is kind of interesting that the neutron is ever so slightly more massive than a proton, and lo and behold, an electron plus a proton equals the relative mass of the neutron. And that actually is because neutrons have a tendency to undergo what we call a nuclear decay and become a proton plus an electron. And I'm going to use this symbol for an electron. And all neutrons can possibly do that. By the way, not only do you have your symbols with the numbers on the left side, but you can also say it like this, where the number 23 is the number in the upper right, or uranium-238 is the number in the upper right, protons plus neutrons. Now, we will be going over math problems and so forth in class. Now, if you change the number of atoms, obviously you change what element it is. If you change the number of electrons, you create an ion of that atom. We'll talk more about ions later. Ion, in case you forgot, is I-O-N. And an isotope is what you get when you change the number of neutrons. Neutrons have a mass, so you're changing its mass, but neutrons are neutral, so they don't have a charge, so you don't change the charge of the atom at all. And it turns out, something Dalton did not know, that just about every atom has multiple isotopes. Some of those isotopes are naturally occurring, and we've learned in the last 100 years that through nuclear reactions, you can also create isotopes that do not naturally exist on the planet as far as we know. So you can have naturally occurring isotopes as well as synthesized isotopes. And the number of those isotopes, when you add the two up, gives you a combination. You might have 20 and 25 isotopes of a given element, of a given atom, even though only 3 or 4 of them might be naturally occurring. Usually there is one predominant isotope, and then the other naturally occurring isotopes are not as common, but sometimes you have a relatively even mix of isotopes for certain atoms. Now, the next thing we should point out is that sometimes we have special names for these isotopes, particularly with hydrogen. So protium is actually hydrogen 1, deuterium is hydrogen 2, and tritium is hydrogen 3, meaning you have 1 proton plus 0 neutrons. For deuterium, you have 1 proton plus 1 neutron, and for tritium, you have 1 proton plus 2 neutrons, because to have 1 proton means to be hydrogen. And of course, you can make compounds out of these different isotopes. You can have H2O, obviously that's the most common by far and away, but you can also have D2O, and you can even have T2O for tritium. And even that, you can have DTO, for example, where you have 1 deuterium hydrogen, 1 tritium hydrogen, and then, of course, your oxygen. Heavy water, which is a natural component, a very, very small percentage, but a natural component of seawater, is D2O. And it's used in a lot of nuclear-type processes. One thing it can do is slow down neutrons, for example. Now, the abundance of each isotope is something that you should be able to calculate if you know the relative mass, the weighted average of the isotopes, and the masses of each of the individual isotopes. You should be able to go from those masses to their percentage abundance, and you should also be able to go from the percentage of each isotope to the relative mass of the, I should actually say the weighted average of the isotopes. Those are two different math calculations, and again, there are examples in this chapter, and we'll go over those later in class, and you might remember them from last year. Next, determining the atomic mass and the isotope abundance obviously is going to require a piece of diagnostic equipment. And this piece of diagnostic equipment is called a mass spectrometer. And in my room, you'll see a poster because that's what I worked on for 12 summers in a classified facility doing government research. The focus of our research was primarily the detection of extremely small quantities of chemicals on the surface of things, particularly the degradative products of chemical weapons. And I'll be referring to some of my research there as much as is possible in the year to come. Nowadays, as mentioned before, we use carbon-12 as our basis for our relative mass. So carbon-12 is defined as exactly 12.000000 till the cows come home, and all the other masses are based upon that. Here's a schematic of a mass spectrometer. There are different kinds of mass spectrometers. My mass spectrometer was very, very special in that I could detect both negative and positive ions. The one that you're seeing here pretty much can only detect the presence of positive ions. But the first thing you have to do is to vaporize your substance, which is relatively easy to do in a vacuum. And so that's why you have, this is usually done in a vacuum. And then you need to zap it with a beam in order to ionize it. And then you get all of your ions. Here's your electron gun. My mass spectrometer did not use electron gun. It used the renate ion gun. And I shot this beam of renate ions at the gaseous stuff, and it knocked electrons off, creating ions, and then those ions enter a magnetic field, which causes it to be deflected. And then, of course, the more massive particles are not deflected nearly as much as the less massive particles are. And then you run a scan across your mass to charge ratio, and every place you get a peak, like right there, means you had a whole lot of a particle that had a mass of 20. In this case, this would have been an isotope of neon. And you can see the lesser isotopes here. This is called a mass spectrum. And I spent hours and hours over those 12 summers, from 93 to 2005, looking at and interpreting mass spectrum. Now, atomic weight, this is an unfortunate use of the word weight because we usually think of weight as mass times the acceleration due to gravity, 9.8 meters per second squared, from physics class. So the atomic weight really is the atomic mass, but it's the average mass of those isotopes. Sometimes we call it the weighted average. It's just like if you were to take a quiz. The class average would be the weighted average, meaning if you had 10 students who all got a 22 out of 25 and one student got a 23 out of 25, the weighted average would be pretty close to 22, but just a little bit more because somebody got a slightly higher score. So the weighted average would almost always be a whole number dot and then some decimal places. So the most commonly occurring isotopes would have the greatest weight in the overall weighted average. And here are some of the relative isotopic masses for the 3 major isotopes of hydrogen. For the 2 major isotopes of boron, you can see that this is approximately 4/5 and 1/5 in abundance here. You can see on neon, it's about 90%. It is just over 90% for neon. For magnesium, most of it is magnesium-24. Most of neon was neon-20. Now, every time you see the atomic mass number, the atomic weight on the periodic table, if it's in parentheses, it's because it's radioactive and not very stable, which means it's hard to pick up a few more significant digits past the ones column. And again, we'll look at math problems a little bit later. And so here's an example of some of the math problems where you, given the percentages, can you find the weighted average? And given the weighted average, can you find the percentages? This case study revisits Ötzi from the introduction to our textbook and how they used isotopic analysis using oxygen-18. The most common isotope of oxygen, of course, is oxygen-16. But they use this isotopic ratio of oxygen-18 to oxygen-16. They also look at strontium isotopes, and they look at argon isotopes, each of which, in God's providence, get assimilated by or concentrate in different tissues of the body and different places in the body, and allows you to draw some conclusions about where this person lived and what he or she may have been eating, and even, maybe what their diet was like and what kinds of diseases they may have had and contaminants that they may have been exposed to. I'm going to stop right there with this particular screencast, and we'll pick up the next one with talking about the periodic table.